Imaginary and complex numbers. We will simplify, add, subtract, multiply, and divide them. Let's start with an equation. We are asked to solve for x and y. Notice the expression on the left, which looks rather complicated, and the expression on the right is in the form of a complex number, a plus bi. A is called the real part, and the other part is called the imaginary part. So what we'll do is we'll set the real parts equal on the left and right side of this equation. X minus 1 equals 5. Let's add 1 to both sides. X equals 6. Now to set the imaginary parts equal, we can set the coefficients equal. Y plus 3 equals 8. Let's subtract 3 from both sides and y equals 5. So that's just an example of a type of equation you could solve related to complex numbers. In this example, we're asked to rewrite in standard form, in other words, standard complex number form of a plus bi. Right now, the radical that you see, negative 27, is not simplified. There's two reasons why it's not simplified. Number one, we have a negative sign underneath there, and number two, 27 can be rewritten as 9 times 3, where 9 is a perfect square. So notice we've expanded negative 27. Let's identify that we can take the square root of 9 out of the radical, and we can take the square root of negative 1 out of the radical. So out of the radical comes 3i. What's left in the radical is 3. Now we're going to simplify this finally by just writing it with the I coming last. So the original expression can be rewritten as 2 minus 3 root 3i. Oh, your turn to write some numbers in standard form, remembering we want a plus bi. So there are 3 examples here, and in some cases you may need to have 0 as part of your expression. Give these a try. The first one, what we want to do is we want to rewrite I squared as negative 1. Now my real part should come first and the imaginary part should come second, so this expression will be negative 1 minus 6i. In the second example, we have the real part, we just need the imaginary part. There is complex number form equivalent to the given. In the third example, we need to rewrite the radicand as a perfect square times something times negative 1. So we'll write it as 9 times 2 times negative 1. Let's take the square root of 9 out of the radical, take the square root of negative 1 out of the radical. What's left inside is 3 times I times the square root of 2. We'll rewrite it as 3 root 2i, but to be technically a complex number, we need a real part, so we'll call this 0 plus 3 root 2i. So those are kind of the building blocks that we need in order to operate with complex numbers. We're asked to add or subtract these complex numbers and to write our answer in standard form. The first example is subtracting. Notice we don't need the first set of parentheses, but the second set of parentheses is important because we need to distribute that minus sign to both terms. Now let's combine our real parts, 8 minus 4 being 4, and we have 4 plus 0i as our final answer. Now you'll notice what's happened in the second example. We've rewritten the square root of negative 8 in expanded form. We've done the same thing for the square root of negative 50. Let's look for ways to simplify these radicands now. We will evaluate the square root of 4 and the square root of negative 1, leaving 2 inside the radical in that first addend. In the second addend, we'll take the square root of 25 and we'll also have an I, leaving 2 inside the radical in the second addend. So let's rephrase the expression this way. Negative 2 plus 2 root 2i plus 5 minus 5 root 2i. We can now combine our real parts, negative 2 plus 5 being 3, and we'll combine our imaginary parts, and our answer will be 3 minus 3 root 2i. That's how we add and subtract. We multiply complex numbers kind of like we would binomials. We treat these, even though these are numbers, we treat them the way we would when we multiplied binomials together using FOIL or double distributive or box, right? We want the answer in standard form. So for the first example, let's think about the FOIL method for multiplying binomials. The first two, right, would be 3 times 1 or 3. The outer two would be negative 2i. The inside two plus 3i. The last two minus 2i squared. Now we look for ways we can simplify this. We know that I squared is negative 1. We can combine our, let's go ahead and multiply the negative 2 times negative 1 there in the last term. And now let's combine our real parts and our imaginary parts. So our final answer will be 5 plus 1i. In the second example, we are simply going to distribute the 6i to both terms. And now we'll multiply our real coefficients. And we'll also remember that I squared is equal to negative 1. So we will now rewrite this in standard complex number form with the real part coming first. That's how we multiply complex numbers. Now to divide complex numbers, we want to think about this the way we would with radicals. Remember how we could not have a radical in the denominator because we would always have to rationalize the denominator? Well, there's something similar going on here. We are not to leave any imaginary number in the denominator. Therefore, to rectify that, let's multiply this expression by the denominator over itself. So now my new equivalent expression will be 6i over I squared. We know that I squared is equal to negative 1, so my final answer is negative 6i, or technically in complex number form, 0 minus 6i. So remembering you can't have an I in the denominator, what we did was we multiplied by a disguised form of the number 1, I over I. Same thing with complex numbers. Complex numbers are not allowed in the denominator. So we are going to multiply by the conjugate. So the conjugate of a minus bi would be a plus bi. And we're multiplying by 4 plus 5i over 4 plus 5i. So with our numerator here, we're going to distribute, and we get 16 plus 20i. And our denominator we can rewrite as negative 25 times negative 1. That will be rewritten this way. My denominator is 41. My numerator is my complex number. This is a good answer. If you wanted to write your answer as a fully complex in proper form, we can do 16 over 41 as the real part, plus 20 over 41i as your imaginary part. So remembering when you have a complex number in the denominator, you must multiply by the conjugate over itself.